Unit 5A, which is the force aspect of an object with 2D motion. This is a fairly significant unit because there's a lot to talk about, because I talk about projectile motion and circular motion. So this video is either going to be quite long, or I'm going to break it up into 2 videos. So basically, I start off with talking about projectile motion. Projectile motion is simply motion in just the x and y. It might be moving to the side, it might be going up and coming down. When an object is experiencing projectile motion, the force of gravity is the only external force acting on it. Keep in mind, if it's just going straight up and down, that's somewhat considered a projectile. I classify that in my projectile motion if it's simply in a free fall. It's just that it has no x component to it. So one of the important rules is what I call, and I didn't make this up, it's the Vegas rule. I know a lot of people talk about it this way. And what the Vegas rule is with projectile motion is what happens in the x stays in the x. Now, and what happens in the y stays in the y. What this means is the vectors in the x and the vectors in the y are independent of each other. And this is critical to understand. The x component of the motion has nothing to do with the y component of the motion. They're independent of each other. When we do projectile motion problems, we use the kinematic equations. They're great. We can simplify them down. So instead of x, we plug in y. For the acceleration in the x, I plug in g. Now I use, and I want the kids to use, -10 meters per second squared. They sometimes get confused with this value of g. When do you use -10 meters per second squared? When do you use 10? My basic rule to them is, if you're using the kinematic equations, it's -10 meters per second squared because g is a vector. Now, oh, I just screwed it up. I said the acceleration in the x. There is no acceleration in the x. It's the acceleration in the y, because g is up and down. I messed that up big time. The acceleration in the x is 0. And so, that because there is no acceleration in the x. Now let me clarify. With our problems, we don't have acceleration in the x. You can. If you have a rocket like in some of the cartoons, the rocket-powered roller skates, and you shoot off the cliff, that rocket is pushing you forward. You could have an acceleration in the x. In the problems that we do in the AP Physics 1, we don't. And so right away, there's no acceleration in the x direction. That greatly simplifies our calculation, which means the velocity in the x is a constant. Change in x is the velocity in the x times time. This is the only calculation in the x direction we do with projectile motion. So let's look at the various scenarios with projectile motion. Now, one very simple scenario is you just simply throw it up and down. And that's a free fall problem. You have a positive y velocity, or you have velocity in the y is 0. It just simply drops. It's 1D motion. That's talked about that in Unit 3A, I believe. And so I'm not gonna talk about that here again. We want to look at, we have motion in the x and y. And so one idea is that our initial velocity in the y, in all these cases, we have velocity in the x. The question is, what's our y velocity component? And so let's say we have a negative initial velocity in the y, that is, it's downward, negative, downward. An example might be we're on top of a cliff and we throw an object forward and down. It has a component in the x direction. It has a negative component in the y direction. Okay. Let's say our velocity in the y is positive. So we're going to throw it upward. Now there's different scenarios here. We can be on level ground and we can throw it upward at an angle. And so like you're kicking a soccer ball, it's going up and coming down. This is a very popular scenario to look at. Let's say my typical problem is a cannonball or maybe kicking a field goal. Well, we're kicking it off the ground upward, but we have to see if it goes a certain height. And then, of course, we have the scenario where we're on a cliff and we throw it upward. And so it's even going higher and off to the side. And then we have no horizontal, no vertical velocity initially. It's all horizontal. This is the most common situation that we run into. We're above the ground and we're throwing it horizontally. This is very common, and this is the problem that probably 90–95% of the time that we run into. The other one is this. We're on level ground, it's thin, and you just have to understand the kinematics associated with this. So when we're running into the horizontal thrown problems, the horizontal projectile motions, if we know h, or delta y, we know h is 1/2 gt squared. This simply comes from the kinematic equations. When initial velocity in the y is 0, that's my acceleration in the y. And so here, it's real easy to solve for time. Time is 2 times h over g square root. This is a very common question. How long is it going to be in the air? And it doesn't matter what the x component is. It doesn't matter how fast you throw it off to the side. It's in the air for the same amount of time because it only depends upon that height. And of course, the acceleration due to gravity. And then delta x, our horizontal displacement, is our initial velocity in the x direction, which is how fast we throw it times time. These are the only equations we have. Now we could look at the velocity when it hits the ground. That gets a little bit more complicated, but this is the most common scenario. I give this to my kids probably 80–90% of the time on quizzes and tests. I give all of them some practice with all of them, but these two problems are the most common. So let's look at a few tips or some things to keep in mind when we're doing projectile motion problems. And some of these I've already mentioned. The acceleration in the x direction is 0. As I said before, for the problems that we do, this doesn't have to be the case, but for the problems that we're going to run into, this will always be the case. If you look at the kinematic equations and set acceleration equal to 0, the only thing that we can calculate is delta x is my initial velocity in the y times time. And so the velocity in the x direction is a constant. Very common question that they ask. The acceleration in the y is g, which is equal to -10 meters per second squared. Yes, you can use -9.8 meters per second squared, but you don't need to, because any problems, any questions on AP exams use -10 meters per second squared. This is the only time you need the negative sign. Any other time when you're using g, like in the gravitational potential energy expression, we just use 10. So that tends to be a little bit of a common confusion point with my kids. The velocity in the y direction is going to be 0, and this is really important to understand, only when it's at the peak. This is the only time the velocity in the y direction is going to be 0. So if you throw it upward, when it gets to the peak of the path, velocity in the y is 0. It still has a velocity in the x. If I throw it horizontal, that's the peak. Velocity in the y is 0. It still has velocity in the x. Very important idea to keep in mind. Remember that when we take a square root, and some of this is stuff that we might have learned from free fall problems. The square root has two answers, plus and minus. Calculators only tend to give us the positive answer. But if an object is going downward, and we're using that v squared kinematic equation, when we take a square root, it might say the answer is 5 meters per second. But since we took the square root, it can be plus 5 meters per second or minus 5 meters per second. We want that negative 5. When we're throwing the ball upward and it's landing at the same spot, like on the level ground. So when we're doing a problem on level ground and we're throwing it like that, time up is equal to time down. Now, this is because we assume no air resistance. If we had air resistance, this isn't true, which is sometimes a little twist on the problem. But 99% of the time, there's no air resistance, and so the time it takes to go up is equal to the time it takes to go down. If you're throwing it off a cliff, this is not true. Not at all true. Now let's talk about uniform circular motion. I kind of break this topic up into two: uniform circular motion and circular motion. Uniform simply means it's going in a circle at a constant speed. So this is a horizontal circle, basically. But let's think of it this way. The net force acting on an object is going to be the sum of any radial forces plus any forces that are tangential or parallel. So tangential, parallel mean the same thing. Radial, so this is parallel. And I can't spell. And radial means perpendicular forces. They mean the same thing. So we can extend this to acceleration as well. So our net acceleration is radial acceleration, which is what we call centripetal acceleration, which is a result of a centripetal force, plus a tangential acceleration, and I'm just going to write it as a tan because I'm lazy, which either speeds up or slows down. So this component is going to speed up, slow down. Because the parallel force is either pushing it along or holding it back. And so the parallel force, which results in a parallel acceleration, tangential and parallel mean the same thing, cause the object to speed up or slow down. Radial forces, perpendicular forces, which result in a radial or perpendicular acceleration, cause it to change direction. These are my centripetal acceleration and centripetal force. So AC and FC, centripetal force. So I don't get into the derivation because quite simply it's not necessary. But the centripetal acceleration is v squared over r. V is its velocity. This is called, sometimes referred to as the tangential speed. Simply, how fast is it going? If it stopped moving in a circle, it's going to start traveling in a straight line at this speed. That's why it's referred to as the tangential speed. It's going to move off into a tangent at that velocity. This is our turning radius. So This equation is on the formula sheet. So centripetal force, and force is just mass times acceleration, is mass times centripetal acceleration, or mv squared over r. This equation is not on the formula sheet, but they should be able to figure it out. So all this stuff over here with the tangential acceleration, tangential force, this was covered in Unit 3. So this information they've already been exposed to. It's this information right here that is specific to this unit. And keep in mind, the centripetal force, which is the sum of all our radial forces, does no work on the object because it's perpendicular. Centripetal. So let me just talk a few minutes about centripetal force, and let's fill in a little bit of detail. Not a whole lot, but let's just kind of tell you a little bit more of certain aspects about the centripetal force. It's not a new force, meaning like on a free body diagram, there is no force labeled centripetal force. Normal force is could be a centripetal force. Friction, tension, the force of gravity. Forces that we've already talked about might be the centripetal force. What makes a force centripetal is its direction. And so there's on a free body diagram, has no force labeled centripetal. And probably looking at an example of this, again, the nature, the direction of the force is what classifies it as centripetal. Everything else stays the same. It's the sum of all radial forces. Everything turns with a turning radius. Now, it doesn't have to make a full circle. When you're driving down the road and you take a left-hand turn, you're turning 90 degrees. And so that's part of a circle. That part of the circle has a turning radius. Any forces along that turning radius, that's what I mean by radial forces. Force is a vector. And so when we look at forces, we have to specify whether it's in a negative or positive direction. I tell the kids the force is positive if it points towards the center of the turning circle. And we'll look at some examples of this. The force is negative if it points away from the center. Don't confuse a negative force as what's called a centrifugal force. There is no such thing as centrifugal. That's simply inertia. But we can, depending upon the style of circular motion, we can have forces pointing away from the center, and we're going to look at those in just a minute. So let's look at a couple of examples with circular motion. And this is going to be pretty busy, and I'm going to apologize in advance. Let's say the object is traveling in a horizontal circle. With a horizontal circle, we typically call this uniform circular motion because the speed is going to be constant. Not that that's overly critical to know, but FYI. Examples of horizontal motion is a car going around a flat curve. The curve could be banked. That complicates the problem. They need to understand how to work it, but I'm not going to get into that example. So let's say here's our car, and then here's our free body diagram, and the car is going around the curve, and I'm looking behind the car. And so looking behind the car as it's going around the curve, we have a gravitational force going down, we have a normal force going up, and then it's turning. Well, the force that's causing the car to turn is the force between the car tires and the road, which is friction. And so let's say the frictional force is pointing that direction, which means the car would be going like that. So the way that this plays out is this frictional force, since we're looking behind the car is moving forward but going off towards that direction. And since this frictional force is the force that's perpendicular to the car's motion, this is providing our centripetal force. So the frictional force is equal to the centripetal force. Frictional force is mu Fn. Frictional force is mv squared over r. We solve for whatever we're being asked to solve for. A different example, still a horizontal example, let's talk about like a tether ball. If you're not familiar with tether ball, it's what I used to play in elementary school. It's a pole, ball attached to the pole with a string. You try and wrap the ball around the string. By hitting it one way, the player hits it, as the other guy hits it in the other direction. Pretty straightforward. So we have the ball as it's circling around, gravity is pulling it down. The tension might be at an angle. But it's going in a horizontal circle. And so it's only a component of tension is providing the centripetal force. And so it's these, now obviously on a free body diagram, remember we don't draw component forces. On a free body diagram we don't draw the component forces, but keep in mind in both cases I don't have anything labeled FC. I'm using the standard forces that we have. And so we can break the problem down here. We need to know the angle or something to break it up into the component that's causing that centripetal force. Now let's look at vertical circles. Vertical circles are a little bit more complicated. Vertical circles do not exhibit uniform speed because the object speeds up as it falls down, and as it goes up it slows down. But it does have circular motion. And so there's a couple of different problems that I tend to talk about. I talk about a Ferris wheel problem. With a Ferris wheel, you're going around in a circle. That's a horrible circle. But you're going around in a circle, but you're always upright. That's the person sitting there. Horrible diagrams. If we look here at the bottom of the Ferris wheel, the forces acting on the person is gravity, and then the seat pushing them up, normal force. The turning circle right there is in the middle of the Ferris wheel. And so here we have multiple forces along the radial. So here at the bottom, our overall centripetal force is the sum of the normal force and the gravitational force. Normal force is positive since it's pointing towards the center of the circle it's going. Gravitational force is negative since it's pointing away from our turning point. At the top, we still have gravity pulling it down, the normal force going up. Apologize for the messiness. At the top, the centripetal force, in this case, is gravity, which is pointing towards the center of the circle, minus the normal force. And so you can see that the direction of my forces are changing with respect to the turning point, which causes a change in centripetal force, which is why we don't have uniform circular motion. So this is the unique aspect with vertical circles. You need to be aware of where in the circle we are so that we can correctly identify what forces and their direction compose of or make up the centripetal force. And then we have the roller coaster, where we're coming down, and here at the bottom we're upright. At the top, though, we're upside down. Well, the forces at the bottom are the same as at the bottom of the roller coaster, since we're upright, or as a Ferris wheel, since we're upright. Gravity is down, and the normal force is up. But up at the top, though, a little bit different. Gravity is downward. Gravity is always downward. But the normal force from the feet is also downward. So our centripetal force at the top is the normal force plus the gravitational force. And so you've got to be very careful about the direction of these forces. The vertical problems tend to be the trickier problems to look at. The horizontal problems have some very neat aspects about them. But these, you got to be careful about the direction of the forces and how to determine the centripetal force. Okay, let's look at a couple of aspects about centripetal force. So let me call this centripetal force tips or reminders. This gets into some of the conceptual ideas of centripetal force. mv squared over r. This centripetal force is the minimum force required for some mass to make a turn with radius r at velocity v. The minimum force, and that's what tends to be confusing. I can have more force available, fantastic, but this is the minimum force for this mass to make this turn at that velocity. So let's think about a car on turn. Kind of already said that frictional force, that's our available force. Mu Fn. This is how much force we have available. All of that force does not have to go into turning the car. It can, but it doesn't have to. So let's say our frictional force is equal to centripetal force. Mu Fn is equal to mv squared over r. So what this gives us is, and we solve this, and we're going to see masses cancel out. What this tells us is that all the frictional force, all the available force, goes into turning the car. If all the available force went into turning the car, we can get the maximum velocity to safely make that turn. That tends to be the question. How fast can we safely do this turn? This is the idea of the road sign. Turn ahead, 35 miles per hour. Now we know we can actually go faster than that because there's some conservatism built into the number, but if you go too fast around that curve, you start losing control and your tires start skidding out because you don't have enough frictional force. You don't have enough available force for that velocity and turning radius in that car. You need too much centripetal force than you have available. So that's the idea. It slows you down. This idea of centripetal force and what it means, sometimes it gets overlooked, but I think conceptually it's really important to understand it's the minimum force for an object of mass m to make some turn at its specific speed. With the case of the car on the turn, the frictional force is the available force. And if all that available force went into turning the car, we can get the maximum safe velocity. So those tips and reminders were more for a horizontal motion. Let's talk about something going in a vertical. And a lot of times the question, like on a Ferris wheel, car going over a hill, a roller coaster as it's going around, a lot of times the question becomes, what's the minimum, maybe the maximum velocity to make that loop. The minimum velocity for the roller coaster to completely make the loop, the maximum speed a car can go over the hill to stay on the road. And when we look at these problems, it is a centripetal force problem, and we set up and we look at the direction of our forces and we figure out what our centripetal force is, and then we say, let the normal force go to 0 so that the car is no longer in contact with the road. What's that speed associated with that? So that the roller coaster is not pushing the rider down. What's the speed associated with that? So let's say we're on the top of a Ferris wheel, we're upright. Or this would be a car going over a hill. The centripetal force is gravity minus our normal force. If we let the normal force go to 0, then the centripetal force, mv squared over r, is simply equal to mg. This is the maximum speed to go over the hill to maintain contact with the hill. If we're on a roller coaster, and so this is a loop on a roller coaster where we're upside down, the centripetal force here is gravity plus the normal force, because the seat's pushing us down. We let the normal force go to 0, we get a similar expression. Be very careful. Kids tend to just simply memorize these expressions, and of course by now you should know that in Physics 1 you can't memorize, you have to learn, you have to explain. And so just because these expressions are the same thing, we end up with the same term for velocity for both of them, root rg. In one case, this is a maximum velocity for the car to go over the hill to stay on the hill. This is a minimum velocity to make the loop and stay in contact with the seat, or for the rail to stay in contact with the car. So even though it's the same calculation, two completely different concepts. Okay, the last thing with 2D motion that I want to mention. It gets into, and this is a little bit almost off topic, but it's still circular motion, and that's with a circular orbit. I know orbits may not technically be circular, but they're pretty darn close to circles, and this is the only type of thing that we deal with. So let's say that this is Earth, and we've got the moon out here, and we know the moon is going around the Earth, and the only force acting on it is the force of gravity between the Earth and the moon. This gravitational force is providing the centripetal force. So this force of gravity is providing the centripetal force. Now this is our universal gravitational force, or G, mass of the Earth, mass of the moon, r squared, distance between centers, is equal to the mass of the moon, v squared over r. And what we can see is we have some simplifying that can take place. And so we can get the velocity of the moon, and this is kind of the interesting aspect. The velocity of the moon, v squared, is g, is only based on the mass of the Earth. The mass of the moon can double, its velocity won't change, and so the velocity of an orbiting object is dependent only on the mass of that center object and the orbital radius. That's all it's dependent upon. So that's kind of an interesting aspect. If we're talking a uniform circular motion with this orbit, the velocity is constant. Well, the velocity, when we're dealing with constant velocity, is distance divided by time. The distance is the circumference, 2 pi r. The time for one full revolution or one full orbit is the period. So a lot of times we have to mix in, we combine these two expressions. And this gets into some interesting aspects on terms of what's going on with these circular orbits. I'm not going to get into a ton right now. These relationships you do need to understand. You do need to be able to do the algebra. But this is like the last little topic area of 2D motion. I got through all my notes. I apologize for this being long. I apologize for talking so fast in some cases. I just knew I had a lot of stuff to cover. There's a lot of information, practice problems that I did not cover that's important to do. But I think these are the highlights for what we run into in AP Physics 1. I hope this was some help. Good luck.